Okay, so I'm Sommer from Team MTSS. So we will introduce our team solution about past and future player contact detection. So first of all, so thank you for hosting this competition. So we enjoyed very much, and it was a really exciting competition. So we tried a lot of things. So I will explain here. Okay, so this is today's topics. So first, sorry, maybe. So can I share again? So okay, maybe my so my pointer is maybe this disappears. So okay.
No problem. 大丈夫です。
Thank you, thank you. So do you see my pointer? Okay, so okay, so this is today's topics. So first we will talk about our background, but we already introduced. But then so move on to the solution part. Okay, so first let me introduce our team. So I'm Sommer, and they are my teammate. So I remember, so in the middle of the competition, so we were very close in leaderboard. So I decided to team up with them. So we are all from Japan, and some so we have some knowledge about computer vision, or right, make sense? Okay, so this is brief summary of our solution. So we use two-stage approach. So that is neural network and gradient boost decision tree. So for first stage, so we use CNN and RNN end-to-end model. And also we perform the multi-frame inference. So that means like 16 frames prediction in a single forward pass. And for the second stage, so we combine output from first stage with tracking data, then train the gradient boost decision tree for utilizing all tracking information. Okay, so this is about architecture of stage one. So I will explain the detail in later slides, but okay, so before that, so let's take a quick look at whole architecture. Okay, so there are three input parts: sideline sequential images and end zone sequential images and tracking sequential images. Not images, tracking data. So we first extract image information by this CNN, and this is a temporal spatial module, and then so concat image and tracking features. Okay, so at the end of this architecture, this feature goes through 2 by LSTM, and finally we can obtain so n. It's the n frame output. Okay, this is training strategies for stage one. So we use these parameters for training. So first, tracking data. So we experimentally select these 10 features, and too much or too less was not good. And for input images, so we use frame -1 and frame +1, and also bounding box position images. Then so we concat these three images, and this time, so we have 3 by 128 by 128 images. And we did same things to so continuous. frames. And finally, we got n by 3 by 128 by 128 images for both sideline and end zone. Okay, then we apply data augmentation like flip, shift, rotate, and so on. And crop size is about 3 times of helmet bounding box width or height. And we have to mention that randomly drop frames like this rate is most important part to train our model because it easily overfitted without this. Okay, so this is sequence and stride we use to infer multi-sequence at once. And so, for example, so this is the tracking data of this player and this player. And so this notation indicates sequence and stride like this. This is a sequence and this is stride. And stride means sequential interval between data. So we first use this sequence, and then we have this stride, and then we use this data, and so on. Okay, so we use same sequence and stride for training data, and small stride for small stride, and also overlapped stride for inference phase. I think this is like a ensemble, because so when we look at this frame, so this frame is near the center of the first data, but so it is also the edge of this next data. So there are many positions for the one frame. Okay, so next second stage, so GPDT part. Okay, we use two models, large GBM and XGBoost. So we filter data by distance less than or equal to 2. And also we change player 1 and player 2 feature because there is no direction, and we doubled data. Okay, and finally, averaged swaps and original prediction. Okay, so here's a feature we use. Okay, raw values from competition training data, and as well as first stage outputs. So I mean this CNN plate. This is a first stage logic. And also we used helmet data. And I think, yes, this helmet features is from this great notebook. And we also use simple computational features. So this means simple absolute difference and product of the features between players, and also difference from the average of all players in each frame. And we use aggregate features for distance, CNN plate, and SA, and speed. Okay, so we aggregated these features for gameplay with position and player and team and step. Also, so we aggregate for the gameplay player 1 and player 2. So also we use shift and so diff for gameplay player 1 and player 2. Okay, so and so using these features, so we fitted so gradient boost decision trees. So for example, so this is let's next 50 for the first stage and right GBM for the second stage, and this shows the top 30 features. And as you can see, so there are many so CNN press. So that means features from the stage 1 and some distance. Yeah, here distance, frame, and so on. Yeah. Okay, so this is because so our first stage model is so enough powerful. So CNN prediction dominates feature importance. So I will explain about this in the later section. Okay, so let's move on to the result. Okay, so these are some example of single model summary, single model score summary, and this is models, sequence stride, and first stage CV. So CV here is 5 average score. So only data for distance, so less than or equals to 2. And also this is a second stage CV, and this one is a private score of the first stage. Okay. So we found our best result is let's next 50, and okay, let's see. So mostly so long sequence like here shows a good CV in the first stage, but so we observed the very small gain in the second stage. And for the shorter model, it shows worse CV in the first stage, but big gain in the second stage. Okay, so and for about the private score, so maybe due to so there are very small fraction of this data set, so there are very large difference. So compared to our local CV. Okay, so here I show you the final ensemble result. So at last, so we used these 6 combination of sequence, backbone, and GBDT. And each line has so 5 folds. So totally 30 models we use. And for the model selection, so we use this forward selection. And yeah, for selection is like this. It's very it's difficult to explain, but anyway, so we use this forward selection, and finally we selected these 6 models. So, okay, so and finally, so we got a very good result in the. This is a public readable, and this is a private readable. Okay. Okay. So CV in this time, so okay, all data. So it's really confusing. So sometimes we check all data, and sometimes we check distance less than 2. Okay, so then go to the findings. Okay, so first I will show you interesting findings. So as I explained, so the longer the sequence length, the higher CV in the first stage. But the shorter the sequence length, the greater the gain of the second stage. So we observed, so as the first model became stronger, so there was less gain in the second stage. I think this is very similar to the second place solution. And finally, so our ensemble submissions were really robust. Robust means private and public score is almost very same score. I think maybe it's due to using different sequence and different backbone. And so I'm now so really happy because we did a great shakeup in the end. And also this is important things, and I think so combination of CNN and temporal spatial module and LSTM is very good choice for our solution. And by using this architecture, so we can do multi-frame inference, and this helps to speed up the training time and also inference time. And also this is very important frame dropout to avoid overfitting. And final point is ensemble. So by this, so we could get a very robust private score by using different backbone, GBDT, and sequence. Okay, and this section is also interesting. So this is what not worked part. So we try to use all 29 this is a whole movie images as a second stage input. But so I try to extract contact occurrence and how many in a frame. And then so I use this input as a GBDT features, but didn't work. And we also try to train player and player ground models so separately, but it's finally so it failed. Maybe so we have to do more investigation. And also, so we found too much or too less tabular features in the first stage. It's not good. It's also didn't work. Okay, so at last, so okay, I will show you the very simple stage 1 model and with a very good score. Okay, so here are the top 4 single models. And okay, so this single models means only the first stage and also 5/4 models. And inference time is only about 1 hour. So but so maybe you can see very good score. So with we only use single model, single first stage model, and by so like this is very very good score. It reaches gold zone, I think. Okay, so thank you for listening. So any question or comment?